Assalamualaikum and good morning. Today we will be on the topic chapter 3, focusing on application retaining wall by using the Eurocode 7 Geotechnical Design and Applications. So the learning outcomes from this topic, students are able to understand design requirement in Eurocode 7 to design retaining wall using Eurocode 7. For example, here this is a flow by using the Eurocode 7 to design retaining wall. For example, you have to identify the design value, the factor of safety, partial factor based on action and effect, and then understand the limit state. Lastly, you have to verify the limit state. Just to refresh back the types of ultimate limit states, there are 5 types. First is AQ, second is structure, third is geo, fourth is UPL, and the fifth is hydraulic. Limit state for earth retaining structure. The following limit states should be considered. Overturning. For a wall to be stable, the resultant truss must be within the base. Most walls are so designed that the truss is within the middle third of the base. And then you have to be considered also for bearing failure. Bearing failure of the soil beneath the structure. The overturning moment from the earth truss causes high bearing pressure at the toe of the wall. These values must be kept within safe limits, usually not more than 1/3 of the supporting soil's ultimate bearing capacity. And then the next state you have to be considered for forward sliding. And the next one is a ground failure. And next is a structural failure. The structural failure caused by faulty design, poor workmanship, deterioration of material, for example. This is the design stage for equilimit state. There are 2 subcategories: destabilizing actions and effect, and also stabilizing actions and effect. So there's a step where you have to add also the partial factors during the design process. This is for geolimit state. This is a example modes of retaining structure failure. For case overall stability for retaining structure, you can see here the slip circle of the failure if you have the gravity wall, and also you have the flexible wall. Okay, again, for gravity wall, the foundation's failure may occur, and then for embedded wall, these some kinds of rotational failures. So the design approach is design approach 1 to be used in Malaysia. What is a design approach 1? It is combination 1, for example, A1 plus M1 plus R1, and combination 2 is A2 plus M2 plus R1. For design approach 1, for retaining walls and shallow footings, 2 combinations are available, except on occasions where it is obvious that one combination will govern the design. The combination of partial factor sets for design approach 1 is different for pile foundation. This is again where you can get the value for destabilizing factor and also the stabilizing factor. What we call it here, for example, unfavorable and favorable. For permanent action G, the variable action Q, and accidental action A. The set for actions denoted by A, material properties denoted by M, and ground resistance denoted by R for each design approach are given in the table below. Also given in the table are the partial factors for the equilimit state. This is a sloping ground of the retaining wall. So there are some sections that we have to consider as a favorable and unfavorable. Favorable here is stabilizing conditions and unfavorable is a destabilizing conditions. So in order to design and analyze this kind of structure, so we have to provide a virtual back of wall here. The principle for the water pressure, principle for structures retaining earth of medium or low permeability such as silts and clay, water pressure shall be assumed to act behind the wall. Unless a reliable drainage system is installed, the principle for infiltration is prevented, the values of water pressure shall be correspond to a water table at the surface of the retained material. So this is the statements where for some kinds of low permeability of soil such as silts and clay, so we're going to assume that the water pressure will be behind the wall. Again, this is a design stage by calculations. For example, you establish design value of action and geometrical data, establish design values of ground properties and resistance, define the limit states must not exceed it, perform relevant geotechnical analysis, and lastly, show by calculation that limit will not be exceeded. For design and construction considerations, the principal design of retaining structures shall take account of the following items where approached. First one is the effect of structure of the wall, including the provisions of temporary support to the sites of excavations, the changes of in situ stresses and resulting ground improvement caused both by the wall excavation and its construction, disturbance of the ground due to driving or boring operations, provisions of access for constructions, and then the next considerations on the required degree of water tightness of the finished wall, and also the practicability of forming ground anchorage in adjacent ground, and then the appearance and durability of the wall and any anchorages. For sheet piling, the need for a section stiff enough to be driven to the design penetration without loss of interlock. So the stability of boring or slightly trench panels while they are open. So these are the some considerations when you design the retaining structure wall. For the Eurocode, in terms of the geometry, the ultimate limit state calculation in which the stability of retaining wall depends on the ground resistance in front of the structure, the level of the resisting source should be lowered below the nominal expected level by n among delta A. So the value of delta A should be selected taking into account the degree of site control over the level of the surface. With a normal degree of control, the following should be applied. First case, for a cantilever wall, delta A should equal 10% of the wall height above excavation level, limited to a maximum of 0.5. So this is the conditions for cantilever wall, where it is given that the delta A must be equal to 0.1 D, or we can say the maximum is 0.5 meter. While for braced wall, For supported wall, delta A should equal 10% of the distance between the lowest support and the excavation level, similarly limited to the maximum of 0.5 meter. So this is the strut, and then the D. The D and the delta A is given by this figure. At rest earth pressure, the principle, when no movement of the wall relative to the ground takes place, the earth pressure shall be calculated from the at rest state of stress. The determinations of the at rest state shall take account of the stress history of the ground. For normally consolidated soil, at rest conditions should normally be assumed in the ground behind a retaining structure if the movement of the structure is less than 5 times 10 power negative 4 times h. For the next condition, a horizontal ground surface, the at-rest earth pressure coefficient K0 should be determined from this formula. The formula should not be used for very high values of over-consolidated ratio. If the ground slopes upward from the wall at angle beta less than the phi internal frictions of the soil effective to the horizontal component of the effective earth pressure may be related to the effective overburden pressure Q effective by the ratio K0 beta, where K0 beta is a K0 times 1 plus sin beta. The directions of the resulting force should then be assumed to be parallel to the ground surface. Okay, this is the conditions where you can use the K0 for horizontal ground surface and also for the ground slopes by adopting the Eurocode 7 design and construction consideration. In Annex C, the limit values of earth pressure on a vertical wall caused by weak density gamma, uniform vertical surface slope Q, and soil cohesion C should be calculated as follows. The active limit states of abrasions at the depth Ka times gamma Z plus Q minus 2C times square root Ka. And then the shear stress at depth Z is equal to overburden A tangent delta plus A, and usually A is neglected. And for passive limit states, the formulas are given here for normal overburden stress at the depth Z and similarly to the shear stress. For mobilized passive earth pressure, this is the value that you might take for considerations. The mobilizations of passive earth pressure of non-cohesive soil versus normalized wall displacement V over Vp, and Vp is the displacement for full mobilizations of passive earth pressure. As the This table shows and gives the order of magnitude of the ratio Vp over H for the full passive earth pressure and in brackets for half of the limit value. The movement ratios in table here should be increased by a factor of 1.5 to 2.0 if the ground below the water table is considered. So this is the example, ratio VA over H and the kind of wall movement. So this where the H is the height of the wall and Vp is the wall motions to mobilize passive earth pressure. This slide shows you examples of design calculation on strength and stability checks by traditional and Eurocode 7 approaches. Given the question, for example, a mass concrete wall, checking on overturning and sliding by Eurocode 7, check the proposed design of the mass concrete retaining wall as shown here. The wall is to be cast into the foundation soil to a depth of 1 meter and will retain granular fill to a height of 4 meter as shown. Take the unit weight of concrete as 24 kN per cubic meter and ignore any passive resistance from the soil in front of the wall. Check the overturning and sliding limit states using design approach 1. So the left figure shows to you a gravity wall subjected to surcharge Q equal to 20 kPa, return field, and also the foundation soil properties are given here, while on the right figure shows to you the earth pressure diagram. Consists of few 1, 2, 3, 4 diagrams. First one, we have to check the overturning. As mentioned earlier, the wall is founded into soil, the ground will contribute to the stability and therefore overturning is checked using the geo limit state. For design approach 1, we must check both partial factors sets combinations. The combination 1 states that the partial factors set as 1 A1 plus M1 plus R1. So the first of all is a design material properties. So again, all these properties value can be seen from the table 5.1 in the textbooks of the elements of soil mechanics by Smith. So it shows here that the retained field, the effective phi is equal to 32 degree, and then the Eurocode 7 states for the concrete wall cast into the soil, delta should be taken as equal to the design value. So for this case, we take the value 1 and the horizontal component of active coefficient is 0.25. While for foundation soil, the effective D is equal to 28 degree. Therefore, the horizontal component of the lateral earth coefficient Ka is 0.3. The next one, we have to check on design actions. The side break of the wall is a permanent, so therefore it is favorable action. Consider the wall as comprising 3 areas as indicated in figure 8.10a, and then the design weight of each area is determined from the cross-sectional area of the pressure diagram. So G1 design for area 1 is equal to 28.8 kN, and area 2 is 129.6 kN, and area 3 is 124.8 kN. So the GW1, GW2 and GW3 are considered as a favorable action, which is acting as the stabilized forces. So the thrust from the active earth pressure behind the wall is a permanent, unfavorable action. It means that this thrust or this force will be considered as a destabilizing thrust. Values of the active earth pressure are indicated on the figure 8.10b. And the active thrust for design field is equal to 48.6 kN, while the foundation soil, the active thrust for design's value is 33.2 kN. The lateral thrust from the surcharge is variable, therefore unfavorable action from the field is equal to 30 kN, while foundation soil is a 9.0 kN. The next one on the design effect of actions and design resistance. The effect of the action is to cause the overturning moment about the toe of the wall. This is resisted by the stabilizing moment from the side flank of the wall. So again, you can see that the area 1, area 2 and area 3 are the earth pressure diagram from the gravity wall being considered as stabilizing action, and the magnitude of the action as given here, and then the lever arm by taking the perpendicular distance to the toe of the wall, 0.53 for area 1, 1.7 for area 2, and 1.3 for area 3 respectively, and the moment is equal to the action magnitude times lever arms. So as you can see from this table, while for the stabilizing thrust or the stabilizing forces is coming from the field, which the magnitude is 48.6 kN, foundation soil in active state is 33.2 kN, while for passive thrust from field is a 30 kN and foundation soil is a 9.0. Again, consider the perpendicular distance which the lever arms taking from the toe of the wall. So we have 2.33 for active thrust for field, 0.48 foundation soil, and 3.0 for the area of the surcharge field, and also the foundation soil is a 0.5 meter. So we have the total moment for stabilizing action is a 397.8 kN, and the stabilizing moments are 2 to 3.4 kN. From the results, it is seen that the limit state is satisfied since the sum of the design destabilizing action and effect is 2 to 3.4 kN is less than the sum of the design stabilizing actions and effect, and by given the over-design factor is equal to 1.78. This also can be designed by combination two approach. So the partial factor set as a A2 plus M2 plus R1. The GEO limit state is satisfied for both checks, and thus the proposed design of the wall is satisfactory. The lowest value of design factor obtained in this case is 1.03 governs the design. Next is example 8.2 on the strength and stability checks by traditional and Eurocode 7 approaches. So we go straight to the against the GEO design approach limit state Eurocode 7. For the overall stability of the wall, once again we check safety against the GEO limit state from the combination 1 and from the table 5.1. So it's given that the unfavorable properties value 1.35, 1.0, 1.5 and 1.0. First, from the design material properties, using the Rankine theory, the active coefficient lateral pressure is equal to 0.238. And then we check on the design actions. In sliding and overturning, the weight of the wall is permanent, so we can consider it as a favorable action or stabilizing force or stabilizing thrust. The influence of the surcharge on the soil on the hill is ignored since transient variable action can never be considered favorable. So there are few sections that we have to consider on the calculation. The first one is the stem base. So for the truss stem we got 46 kilonewton, base we have 30 kilonewton, and the soil on heel is equal to 173.9 kilonewton. Therefore, the total vertical resistance is a 249.9 kilonewton. So the thrust from the active earth pressure is permanent, so this is considered as an unfavorable action or destabilizing action is equal to 72.3 kilonewton. The lateral thrust from the surcharge is variable. It also called as an unfavorable actions. So we have the value is equal to 17.8 kilonewton. The next one we have to design the effect of actions and design resistance. From the sliding, total horizontal thrust is equal to 90.1 kilonewton, and therefore the design resistance is equal to 195.2 kilonewton. Therefore, the design factor or over design factor is equal to 2.17. And then check on overturning. The stabilizing moment is equal to 165 kilonewton meter. For stabilizing moment is equal to 416.3 kilonewtons. So we see that the stabilizing moment is larger than destabilizing moment, and the design factor is equal to 2.52. And then when we check on the bearing, we have the destabilizing moment is 165 kilonewton meter, and for the stabilizing moment, the weight of the wall RV is now considered as unfavorable action and includes the surcharge acting on the soil on the heel. So when we calculate the total moment stabilizing, we have the answer is a 623.4 kilonewton meter, and then the resistance vertical force is equal to 368.9 kilonewton. And get the level arm within the middle third of the base. So we have 1.24. Eccentricity is a 0.26, and the maximum bearing pressure is a 186.9 kPa. And then the over design factor is a 1.34. The same problem can be also designed by Eurocode approach in combination 2, which partial factor sets A2 plus M2 plus R1. The calculations are the same as for combination 1, except that this time the following partial factors from the table 5.1 are used as a unit with G unfavorable is a 1, and then favorable is 1, and Q destabilizing is 1.3, and effective phi is a 1.25. The favorable actions are the same as for combination 1 since gamma favorable is equal to 1. The next one is examples of design calculation for flexible retaining structure, cantilever sheet pile wall. Sheet pile wall are flexible and sufficient yield will occur in a cantilever wall to give totally active earth pressure conditions. Let the height of the wall be h, and suppose it is required to find the depth of embankment d that will make the wall stable. For equilibrium, the active pressure on the back of the wall must be balanced by the passive pressure both in front of and behind the wall. If an arbitrary point C is chosen and it is assumed that the wall will rotate outward about this point, the theoretical pressure distribution on the wall as given previously. The toe of the wall is deep enough such that the conditions that prevail are known as Fitz conditions. In the limit state design method to establish required design depth, the depth D is obtained by balancing the disturbing and restoring moments about C together with the horizontal forces established using the pressure distribution. So, in a Eurocode 7, The geo limit state is applied to assess the rotational stability using this theoretical pressure distribution. The method generates two equations containing the unknowns d and d naught, which are solved by repeated iteration until the correct values are obtained. For example here, cantilever sheet pile wall, calculate the minimum depth of embankment D to provide stability to a cantilever sheet pile wall retaining an excavated depth of 5 meters using Eurocode 7 geolimit state design approach 1. And then the soil properties are given here. So the figure A shows a wall geometry, B is a pressure distribution, and C is a pressure distribution by simplified method. So what we need to find here are D and D naught. And then by taking a moment at the point O. And the problem is illustrated as shown just now. In the Eurocode 7 geolimit state design 1 approach, first for a future unplanned excavation, delta A equal to 10% of the clear height, which is equal to 0.5 meter. The pressure distribution as shown just now, and by using the combination 1, partial factor set A1 plus M1 plus R1, and then the properties from the table 5.1 are given. Unfavorable G unit weight is a 1.35 and then effective fee is a 1.0. And using the Rankine theory, the Ka is a 0.33 and Kp is a 3.0. It is appropriate to use Rankine theory as the steel sheet piling can be assumed to be smooth and thus no friction exists between wall and soil. And thus pressures acting at the salient points in the distribution are established. So behind wall, at least we have PAs at O, PP at O, and PP at B. So you can see that this is one unknown D naught at each PA at O, PP at O, and PP at B. And also in front of wall, we have a similar unknown D naught. And the active thrust due to the earth pressure is a permanent and favorable actions. Active thrust 1, so this is one equation that we have. And then the active thrust 2, the equations with a substitute value obtained from the table 5.1. So we have 4.5 d naught plus d times d minus d naught equal to 4.5 d power 2 minus d naught power 2. The passive pressure is treated as a permanent. So the passive one is we have 40.5 d naught power 2 and passive thrust 2 as shown in this formula. And then the effect of actions, consider the moment about point O. And the force level R moment as shown in this table. By taking moment at O, we have equation 1 and summation horizontal forces for active and passive thrust. This is what we have in equation 2. And we solve equation 1 and 2 simultaneously. We have D naught is equal to 5 meter and D is a 5.3 meter. The same problem can be solved by combination 2. Next one will be example free a support method for anchor sheet pile wall by Eurocode 7 approaches. If an anchor is placed 1 meter below the ground level behind the sheet pile wall described in example 8.3, calculate the minimum depth of embedment D to provide stability using the Eurocode 7 geo-limit state design approach 1 and the gross pressure method taking FP, the factor of safety on passive resistance, as equal to 2.0. And then this is the problem on the left side, and also the right side is the pressure distributions. We have a surcharge 10 kPa on the ground surface, and then we have anchor at point A with the depth is 1 meter from the ground surface. In the Eurocode 7 geo-limit state design approach 1, as before, allowance is made for future unplanned excavation. Delta A equal to 10% of the clear height. This is the height between the ground surface in front of the wall and the anchor, which equal to 0.4 meter. The pressure distribution as shown in the figure just now. So by consider the combination 1, partial factor sets A1 plus M1 plus R1, and from the 7.1 table, these are the values that we have, with the Ka is 0.33 and Kp is the 3.0. So the first one is the design action. We have to calculate the active thrust due to earth pressure. It is a permanent unfavorable actions. What do we have from here? The active thrust design is a 4.5 times G plus 4.4 power 2. The passive resistance is also considered a permanent unfavorable actions. Thus, we have 40.5 D power 2. Next one, we have to consider the effect of actions. D is obtained by resolving the moment equilibrium equation. The lever arms about A. So we have lever arm active is 2/3 D plus 5.4 minus 1, and lever arm for passive is a 2/3 times D plus 4.4, and then by taking moment equal to 0, so we have the next equation here. Okay, what do we have from this equation? We got the D is equal to 2.1 meter, and then the design depth is a 2.5 meter. So the 0.4 is the principal design, with the delta A is a 10%. This is the solutions by combination 2 and the gross pressure method. That's all. Thank you.